Hi friend, this is Shomik Biswas and you are attending my class of circuit theory and network. Our today's objective is the incidence matrix and that loop matrix and the Kath-Zeth matrix. So first of all, I would like to discuss what is incidence matrix, that is AI. Okay. So what is the definition of incidence matrix, how it is being theoretically calculated? Actually it will need a much more deeper in sense, and you have to be much more literate before having such type of theoretical discussion. So in this class it is my objective that I should take you in the form of common mathematical example that you can understand easily what is the concept of incidence matrix. Now I have taken one simple example. In this particular case you can see this graph I have taken. So in this particular graph, how many nodes are there? Yes, that is A, B, C, D. I just marked it with circle 1, 2, 3 and 4. This 3 and 4. So 4 nodes are there. I have written it. Okay. Now how many branches? The nodes are connected with the branches. So first branch, second branch, third branch, fourth branch and fifth branch. So 5 branches are there. So here I have noted this also, that 5 branches are there. Now what is the condition to make one incidence matrix? That number 1, current leaving node. It means in a particular node, if current is leaving the node, so it must have the positive sign. Here see, the current is leaving number 1 node. So with respect to number 1, that coefficient of that particular matrix should have positive sign. And in the other way, if the current is entering the node, this one here, I better write, that is this point, you just see this one. In this particular case, here the current is leaving A. So with respect to A, the coefficient in this matrix should have plus. But the coefficient with respect to B should have minus. Why? Because current is entering to this B. You can see it, the current is entering to this B and the current is leaving A. So with respect to A, the coefficient should have positive. With respect to B, the coefficient has to be negative. This is the basic conception before starting one incidence matrix. Now how to write this incidence matrix? Here I have jotted few points. One of them is called the nodes and another thing is called the branches. So first of all, I have jotted here 5 branches are there, 1, 2, 3, 4, 5. So I just write it here. As you can see, it is 1, 2, 3, 4, 5 in this way. Okay. And in the other section, I have again marked it as the nodes. This one, 1, 2, 3, 4, 4 nodes are there. Now the coefficients are taken. So node 1 here, just come to this. Node 1, actually see this, node 1 to node 2. So the coefficient is A12. Node 2 to node 1 with respect to this. When we are observing from 1, actually how many branches directly affecting by the nodes, you can see that the connection is just like this. 1 is directly connected to 2 and 1 is directly connected to 5. No more other connections. So A 1 5 and 1 2. In both cases the current is just leaving this branch, so it should have positive sign. So actually the node number is 4, so the current is passing 1 to 2, 1 to 4, that is A12 and A14. Now A12, this is lying on branches number 1, but A14 is lying on branches number 5. So under 5 I should write A14, under 1 I should write A12. In the same way, when you are going to this one, so what is A21 when it is going from 2 to 1? So it is A21, and two, there how many relations are there. Here you can see that is in this particular graph you can see that the relations are there in this way that 2 is related to 4, so this one, 2 is related to 3, so this one, 2 is related to 1, so this one. So 3 relations are there. So you are having 3 coefficients A21, A24, A23. See, I have just written that entire thing with that respect to 2. This one, 21, 23 and 24. Again 0, 32, 34, because you can see that 3, here the branch number 3, it is connected with 4 and connected with 2. So 3, 2, 3, 4. So I should write in this way, that is 3, 2, 3, 4, and the last one is in the same way, that is 4, 3, 4, 2 and 4, 1. Now see the direction of the current. So A12 and A14 all should have here plus 1, because that coefficient is taken as 1. So plus minus is decided upon the direction of the current flow. So here A12 and A14 both have plus 1. So accordingly to this, how should I fill up? That is 1, 1. Again A21 is the reverse way, so it should be minus 1, and that A23 it should have plus 1, because the current is not entering, it is just leaving. So in this way you have to fill up the entire matrix as 1, 0, 0, 0, 1, minus 1 for the second node, it is minus 1 plus 1, as you can consider. I have shown you how to get that. Then 0 plus 1, 0. Now why 0 is there? Because in that node 1 there are relation between 1 and 2 and 1 and 5, but no, here no relation between 2, 3 and 4 branches or the nodes. So obviously it should have 0. In this same way you can see it that here A1 to A2 is related, A1 to A4 is related, but not that is A2 to 3 and 3 to 4, there is no relation. So obviously only the A is just applied on that 2 particular nodes. As you can see here you can see this, that A is applied on that 5th number branches and 1 number of branches. So these 2 branches have coefficient and the other branch is not related, so it all should have that 0. Okay, so finally in this way you have to fill up the entire one and you will be getting this type of final matrix. This is the final matrix. Don't make that circle, actually some reason I have made that circle, but you should not make it. You just write either plus 1 or minus 1. So as a whole the entire circuit is called the incidence matrix. Now what is the properties of the incidence matrix? That if you are taking the entries of each column individually, it means if you are taking the entries of the first column, this one, or you are taking the entry of second or third or fourth or fifth in this way, so the summation of the column entry must be equals to 0 always. When you are making one incidence matrix, you should always calculate that whether each and every column entry, if you are summing together, it must be 0. If it is not 0, so obviously you are making something wrong, because it is not the actual incidence matrix. Now another thing is what? That determinant of a closed loop for that AI is always 0. So if you are having one closed loop, if you are making one AI, so that is always 0. So how to get that, whether a loop is closed or not? If you are having one tree, if you are having one graph, so how to decide which one is tree and which one is graph? Just take its incidence matrix. If it is a really graph, means it is a closed loop, so obviously the determinant is obviously 0. I have shown you this. You can see this particular point. This is this particular point I have already noted. So you can see the determinant of A must be 0 for a closed loop, but if it is a tree, it never be 0. Now another thing is coming, that what is that reduced incidence matrix? I told you what is the incidence matrix, but some question may be coming, what is reduced incidence matrix? So to get the answer, actually in the definition of reduced incidence matrix, it is told to that in a particular incidence matrix, if any row vectors, okay, here any row entry if deleted, suppose we have got how many rows like this, here row 4, row 3, row 2 and row 1, so already having 4 row, so any row can be omitted from that particular matrix, and this is called the reduced incidence matrix. So this is a definition actually, but the definition is incomplete because deleting any row doesn't make the same sense. But here what is the concept of reduced incidence matrix, that if you are deleting any one row, it can be one incidence matrix, the result, but the total circuit property and the circuit nature, the circuit behavior has to be exactly same. It means the reduction of that particular row doesn't affect the property of that particular circuit and the nature of the particular circuit. So how to get that? Now if you are having that sort of incidence matrix, you can see it. So here this is the incidence matrix, and by the incidence matrix I am just making one graph. Okay, so how to do this? Just a reverse calculation, or somebody is saying there is reverse engineering. So here we are just getting this coefficient 1, 2, 2, 3, 3, 2, all these are we are collecting from this, and which one I have just collected, I just make it a bubble, okay, from this particular one. That I want to mean here these all coefficients are being calculated from this given incidence matrix. And by the way, A12 equals to 1, so here 1 and 2, two nodes are there, so 1, 2 is plus 1 means obviously the current is leaving this one. Now by the help of a 2, 3 equals to 1, so 2 and 3, this one 1, so current is having this. In this way all the points which is needed to make such type of closed one, I have just make it. So final structure has come like this, okay. It may be quite critical to see. Actually this is a final structure that we are making again, this one. Now see this one, and here the starter one, this one, and the bottom one. Here the configuration, just see it clearly, okay, and the configuration that just I have shown to you, this one, they are exactly same. So on doing this, I have seen that from the graph I need to take only those bubble points, okay. But here it is seen that number 4th entry, this one, is no more required when you are reconstructing the graph from that incidence matrix. So if I omitting this 4th line, it means the 4th row, the total graph will never change its property. So by deleting 4th row, what is the final matrix has come, you can see it. So this is a final matrix, as you can see, this one. Here the 4th row is represented with this dotted line. So that matrix having the dimension of 3 cross 5, where the original matrix is 4 cross 5. So this is basically called the reduced incidence matrix. This one is a reduced incidence matrix. So in this class I have cleared to you what is the concept of incidence matrix, what is the reduced incidence matrix, how the incidence matrix is created, by the help of incidence matrix how can you judge whether a graph is tree or the complete closed loop graph, and some properties, and also the elimination style. It means which row has to be eliminated to make a reduced incidence matrix from an incidence matrix. It is not sure that in each and every incidence matrix can be made as reduced incidence matrix, but if the question arises that whether the reduced incidence matrix is existing or not, so for giving this answer you have to do this type of reverse engineering or the reverse mechanism. If it shown that all the coefficients of that incidence matrix is equally required, to make such graph, so obviously it cannot be reduced more. But if it is seen for this type of example, that if you are omitting the last row, still the sense of the entire circuit will never change. So obviously it is used to reduce the size. One reduced incidence matrix can be given. Now what is the need of getting this reduced incidence matrix? The only reason to change the bulkiness of that entire mathematical process, or if you are considering one more row or two more row in a particular circuit, then it may be quite bulk to calculate the other parameters of the circuit. So if one row or two row is omitted, so the size will be quite squeezed, so it is easy to handle. So in a way, that reduced incidence matrix may be created by the deletion of one row. Maybe in some cases I have seen that more than one row can be deleted to make one reduced incidence matrix. So thank you very much for this class you all have attended. And finally friends, I will go much more deeper on this about the tie set and the card set in my next classes. So see you all early next in my next classes for the discussion of that tie set and the card set. Thank you very much.